Hey everyone, and welcome back to the deep dive. We know you all love to learn quickly and get to the bottom of really cool stuff. And who doesn't love those aha moments? You know what I'm talking about. But without having to wade through a ton of boring details.
Right.
Well, that's what we're all about.
Yeah.
And today we're gonna zero in on something, well, kind of mind-blowing. It's how our brains handle visual stuff, pictures in space, and how that connects to how well kids do in math.
Yeah, that's right. We've been digging through a whole bunch of research, and our goal here is to give you a really solid grasp of how these things are related, like what the science actually says, but in a way that makes sense and keeps you hooked.
Exactly. So the heart of what we're talking about today, it's this thing called Visuo-Spatial Working Memory. Let's just call it VSWM.
Hmm.
And specifically, how it relates to how kids are doing in math,
Yeah.
during those school years. So first things first, VSWM. What exactly is that?
Okay, so imagine VSWM as like your brain's sketch pad. It's the place where you hold and play around with visual information, like, remembering what a shape looks like, or figuring out how different pieces fit together in space.
Okay.
And to really understand this, we need to go back to some foundational research. Baddeley and Hitch, back in 1974, they were the first to propose this idea of a visuospatial sketchpad. They saw it as this key part of our working memory system. And Baddeley actually went on to refine this model even more in 2000.
Okay.
It's basically the system that lets us keep visual and spatial details active in our minds on the fly.
Got it. So it's kind of like mentally picturing those instructions to put something together or remembering the layout of a room, after you've left it. And within VSWM itself, our research points to different ways it operates, right?
Oh, absolutely. We've got researchers like Mamarella and her colleagues. They did some cool studies, back in 2006 and 2013. They highlighted this important difference between simultaneous and sequential VSWM.
Okay, so break that down for us.
Right. So simultaneous VSWM is when you're dealing with all the visual information at once. Like if you were trying to remember a pattern of colors.
Okay, yeah.
Whereas sequential VSWM, that's when the information comes in steps, bit by bit. So like remembering a sequence of hand movements or something like that.
Gotcha. So two different ways our brains tackle that visual and spatial stuff.
Yeah.
Okay, so we're talking about how kids perform in math. The studies we've been diving into, they spotlight two main areas. What are those?
We're looking at what's called numerical operations, and then there's mathematical reasoning. So numerical operations, that's all about those foundational math skills, right? Basic knowledge about numbers, mental arithmetic, being able to calculate things. Geary, along with others, they wrote a lot about how important these are. That was back in 2007.
Right.
And then there's mathematical reasoning.
Mm-hmm.
This is where you take that basic understanding of numbers and you use it to solve problems. Often more complex problems, the kind you find in real-world situations. It's like you're putting that numerical knowledge into action.
Okay.
Thomson offered a pretty good definition for this back in 1996. And we can see some clear examples in Wechsler's assessments from 2017, things like fractions, decimals, understanding graphs, probability, all of that falls under mathematical reasoning.
So it's the difference between knowing how to add and subtract versus figuring out a word problem that uses those skills.
Gotcha. And, like we said at the beginning, the whole point of this deep dive is to really unpack this systematic review, this paper by Allen, Higgins, and Adams from 2019. We want to get to the bottom of what this research is telling us about VSWM and math.
Yes, exactly. They took a deep dive into the findings from so many individual studies. So it gives us this incredibly valuable big picture view of where the science is at on this connection. All right, so let's get into it. Let's go back to the basics here. Where does a child's ability to even do math, where does it all begin? I mean, it's not like they're born knowing this stuff.
You're absolutely right. It's definitely not something you're just born with. Mathematical development, it actually starts way before kids ever set foot in a classroom. It begins with the development of what we call number sense, and also an understanding of this thing called a mental number line.
Okay.
Birch talked about this back in 2005, and Schneider and his team explored it further in 2009.
A mental number line. That's a really cool concept.
Yeah, it is. It's basically like an internal representation of numbers,
Right.
all in order. But hold on. Even before that mental number line fully develops, even before that, there's actually evidence that we have an inborn sense of number. Like, it's hardwired into us.
Really?
Yeah, it's called the approximate number system. Deteen went into this back in 2001. It's our ability to just, without even thinking about it, know which of two groups has more stuff in it.
So it's like a really quick, almost subconscious sense of how much there is.
Exactly. And there's this other ability called subitizing, which is super closely tied to it. Subitizing is being able to just instantly tell how many things are in a small set without having to count them. You just see it.
Wow.
Clements and Ginsberg, they did some interesting work on this. Clements in 99 and Ginsberg back in 78. And some researchers who look at things from an evolutionary perspective, like De Cruz in 2006, they actually suggest that this basic number sense we're talking about, it might have given our ancestors a survival advantage.
Oh, interesting. Like, how so?
Well, think about it. Quickly figuring out which patch of berries has more food, that kind of thing.
That's fascinating. It's like our brains are kind of prepped for numbers from the get-go. So how do we go from that basic, like, gut level number sense to actually being able to do math?
Well, as kids are picking up language, they start learning the counting words 1, 2, 3, and so on. But early on, as Sarnecka and Wright pointed out in 2013, this is often more like just reciting a list from memory, a placeholder structure, they called it. They haven't really grasped what those numbers mean yet. It's sort of like leaving the words to a song without actually understanding what the song's about. The real understanding starts to click when they can connect specific amounts to those written numerals. Like when they realize that the symbol 3 actually stands for 3 things in the real world.
I see. So it's that moment when the written symbol and the real-world quantity finally match up in their minds.
Precisely. And that's when they start to get those fundamental counting principles. Things like cardinality, the idea that the last number you count, that's the total number of things you have. And abstraction, understanding that you can count pretty much anything, even things that aren't physical objects. And one-to-one correspondence, that each thing gets counted only once. And stable order, that we always count in the same sequence. And then there's order irrelevance, realizing that it doesn't matter what order you count things in, you'll still end up with the same total.
Okay, there's a lot packed into that.
Yeah, lots of moving parts. Gelman and Gallistel, they actually laid out all those core counting principles way back in '86, and others like Dehaney and Thompson have added to our understanding since then. And what's really amazing is that the initial accuracy of that approximate number system in babies, that early gut feeling for quantity we talked about, Libertas and her colleagues, they showed in 2011 that it can actually predict how well those kids will do in math later on, like much later on.
Whoa, that's wild. So there's this whole journey from those first little inklings of number to fully developed math skills. So where does VSWM fit into all of this? What's its role?
All right, this is where things get really, really interesting. Ashkenazi and some other researchers, they wrote in 2013 that they see VSWM as a source of domain general vulnerability in arithmetic cognition.
Okay, hold on. Back up for a second. What does that even mean?
Okay, think of it this way. VSWM is like this basic brain skill, a foundation. And that foundation supports learning in a bunch of different areas. And guess what? Math is a big one.
Okay, so domain general vulnerability. You're saying that if someone's VSWM isn't very strong, it could make it harder for them to learn math in lots of different ways.
That's exactly what it's suggesting. And here's where it gets even cooler. The role that VSWM plays in math, it seems to change as kids grow up.
Really?
Yeah, we've got Lynn Geary in 2013 and Holmes and Adams in a whole bunch of studies. They did some in 2006, some in 2008, and then Anderson too in 2008. They've all been hinting at this possible cyclical relationship between VSWM and verbal working memory. It looks like VSWM might be especially important when kids are first learning new math ideas, like when they're just encountering a concept for the first time.
A cyclical pattern, meaning it's not, like, always equally important. That is a huge aha moment for anyone who's into child development and, well, anyone who just cares about how kids learn.
For sure. The idea is that when you're trying to picture a new math concept in your head or, mentally move numbers around in a new way, VSWM is doing a lot of heavy lifting. But then as you practice those skills and they become more automatic, maybe verbal working memory or other brain systems take over a bit more.
Wow, that makes a lot of sense. Okay, so that sets the stage for us. Now, let's really dig into the details of that systematic review by Allen, Higgins, and Adams. Tell me, what exactly did they do in their study?
All right, so they analyzed a total of 35 different research studies, and all of these studies looked at the relationship between VSWM and how well kids were doing in math. These kids were between 0 and 16 years old, and they were all in mainstream schools. They had some pretty specific rules about which studies they included. Like, they only included studies that were published in peer-reviewed journals, and they didn't include studies that focused on kids with specific developmental differences, or adults over 16, or babies who were born prematurely. And they left out studies that looked at brain imaging, math anxiety, number sense by itself, or visual perception without the memory part.
Got it.
They also didn't include studies about interventions like working memory training, or studies that focused on the strategies kids use to solve math problems or teaching methods, or how kids learn to read and write numbers.
Okay, so they were really focusing on a very specific set of studies. So how did they find these 35 studies? Where did they look?
They did some really thorough searches. They looked at all the major research databases, places like Web of Science, JSTOR, ScienceDirect, and Scopus. They used all the relevant keywords, things like Visuo-Spatial, working memory, and a bunch of terms related to math. And they didn't just stop there. They also went through the reference lists in each of the studies they found, to make sure they hadn't missed any other relevant research that might be hiding out there.
Wow, they really covered their bases.
No.
So what did they find when they analyzed all of the data from these 35 studies? What were the main takeaways?
Well, the most important thing they found was a pretty strong positive connection between VSWM and how well kids did in math. Like overall, kids with better VSWM tended to perform better in math. And they actually used something called a forest plot in their paper, which is this visual way that researchers can summarize the results from a bunch of studies.
Right.
It helps to make the overall trend really clear. They also checked to see if there might be something called publication bias, which is this tendency for studies with really exciting or positive results to be more likely to get published, compared to studies with less impressive findings.
Yeah, that's an important point.
So they used a funnel plot and this statistical test called Egger's regression to check for that bias. And what they found was that publication bias was probably pretty minimal in this area of research, which is a good thing. It means we can be more confident that the findings are a pretty accurate reflection of the relationship between VSWM and math performance,
Yeah.
and not just a result of, researchers cherry-picking studies with really strong results.
That is reassuring.
Yeah.
Like, it makes you feel like these findings are legit, right? What else did they discover?
Well, they also looked at the role of sample size, and this is interesting. They found that studies with fewer participants tended to report bigger effect sizes, and they actually found this correlation to be statistically significant. It's something that other researchers like Kuberger and Levine and their colleagues have noticed in different areas of research, too.
Interesting. So what does that mean for this VSWM research?
Well, they were careful to point out that one study in their analysis had a huge sample size, over 4,000 children, and that study still showed a medium to large effect size. So while smaller studies might sometimes show slightly stronger effects, it's not like the whole finding is just based on those smaller studies. The overall trend seems pretty solid.
So the connection seems to hold up, even when you look at studies with lots of participants. What about the specific type of math that these studies were measuring? Did that matter?
Yeah, they actually looked at that too. They categorized all the studies based on whether they were mainly focused on numerical operations, mathematical reasoning, or both.
Okay.
And get this, the biggest average effect size was actually in those few studies that only looked at mathematical reasoning. The next biggest was in studies that measured both numerical operations and reasoning. And then the smallest effect size was in those that just looked at numerical operations.
Interesting.
Now, it's worth noting that these differences between the groups weren't statistically significant. And that might be because there just weren't many studies that only looked at mathematical reasoning. But it does kind of hint that maybe VSWM is even more important for those higher level math skills. The problem-solving stuff.
Yeah, that makes sense. Like you can imagine needing to really picture things in your mind when you're tackling those more complex math problems.
Exactly.
What about the different types of VSWM? Simultaneous versus sequential? Did they look at whether that made a difference?
Yes. They found that studies measuring both simultaneous and sequential VSWM tended to have the biggest average effect size. Then came the studies that only focused on sequential VSWM, and the smallest effect sizes were in the studies that only looked at simultaneous VSWM.
Huh.
This trend was almost statistically significant, but not quite. It seems like maybe the way we're using our VSWM, like whether it's simultaneous or sequential, might influence how strongly it's related to math ability. They also pointed out that there's a bit of a research gap here. There haven't been any studies that specifically looked at the relationship between sequential VSWM and mathematical reasoning.
Oh, wow. That's surprising. You'd think the order of information would be super important when you're working through those multi-step math problems. What about the age of the kids in these studies? Did that seem to matter?
You know what? It's funny. They didn't find any correlation between the kid's age and the strength of the VSWM math connection. It didn't matter if they looked at the kid's age at the start of the study or at the end. The connection was there.
Huh.
Now, the average starting age across all the studies was about 7.9 years old, and the average ending age was around 9.9. But the ages ranged from like early elementary school all the way to high school.
That is a pretty big range. So it sounds like this connection between VSWM and math skills might be pretty consistent throughout those school years.
Yeah, that's what the studies seem to suggest. But the authors of the review, they do emphasize that more research is needed to really nail down how stable this relationship is over time, as kids develop and move through those different phases of learning.
Okay, so more research is always a good thing. One last thing from the review that really stood out to me. They talked about the way those studies measured math ability. Did the specific type of math test they used have any impact on the results?
Oh, yeah, this was a big one. This was a key finding. The review found that using a standardized math test made a huge difference in the effect size.
Really?
Yeah, studies that use standardized math tests, those tests that are really carefully developed and tested to measure specific math skills, those studies reported a much bigger average effect size compared to the studies that used non-standardized measures, like tests that were just made up by the researchers themselves for that specific study.
Wow.
But here's the other thing. They didn't find a difference based on whether the VSWM measure was standardized or not. So it seems like the way you measure math, like how rigorous and standardized the test is, that has a really big impact.
That is a super important point. So it's not just about whether there's a link between VSWM and math. It's about how we measure that link. It really highlights how crucial it is to have really good measurement tools in research.
Exactly. It really underscores how important validity and reliability are. And standardized tests, they're often designed to make sure that you're measuring those core math concepts in a consistent and really accurate way.
Okay, so zooming out and looking at this whole systematic review,
Yeah.
what are the big things we can take away from it? Where does this research need to go next?
The authors of the review pointed out a few key areas for future research. They really stressed the need for more studies to figure out how stable this relationship is across those different grade levels.
Okay.
They also want to see more research on whether this VSWM math connection is stronger for certain parts of math. For example, is VSWM super important for learning about fractions, but not as important for memorizing addition facts? Those are the kinds of more specific questions that future research can help us answer.
Yeah, that makes perfect sense. So for everyone listening, let's bring this all together. What are the key takeaways from this deep dive?
The bottom line is this. There's a pretty clear and consistent connection between a child's visuospatial working memory and how well they do in math. And this connection seems to hold true throughout their school years, but the way we measure math skills, specifically whether we're using standardized tests or not, that really has a big impact on how strong that connection seems to be.
So even though this is still a relatively new area of research, this systematic review gives us a really solid starting point for understanding this link between VSWM and math.
I agree. It shows us that these core cognitive skills are really intertwined with how well kids do in math.
And that leads us to a final thought for you all to ponder. If VSWM is so important when we're first learning new math ideas, how can we use that knowledge to design better teaching methods? Like approaches that really take advantage of that visual and spatial thinking early on. Or, given that we saw some differences in the strength of this connection across studies, what are some other factors that might be at play here? Things about the individual child or their environment that might also influence this relationship between VSWM and math?
Those are some great questions to think about. And for anyone who's interested in learning more, we definitely encourage you to check out some more research in educational psychology.
Awesome. Well, thanks for joining us for this deep dive, everyone. Until next time, keep those brains buzzing.